the color film, Jim? Hand me a roll of color, quick.
Oh, man, that's great. Where is it?
Quick.
One of the great revelations in my lifetime that have come out of science that will be spoken about 3,000 years hence occurred on Christmas Eve of 1968 when Apollo went around the dark side of the moon. And for the first time in human history, we saw not a sunrise or a moonrise, but an earthrise. In that sudden moment of illumination, we saw that we were not an infinite horizon. We were a finite planet floating in the velvet void of space, as the astronaut said. We didn't go to space to acquire new wealth, but to return with a new vision of life itself. And in doing so, the whole paradigm shifted.
Our scientists have now had 50 years to study the shift through this new paradigm and to ask critical questions. What fuels Spaceship Earth? How sufficient are its provisions? What controls its direction? And how long can it sail? This series is about what they've learned.
People say to me, I wonder what it'd be like to be on a spaceship. And I say to you, you don't really realize what you're doing. Because everybody is an astronaut.
Ich denke, die Erfahrung, die ein jeder macht, der, wie ich, die Möglichkeit hatte, die Erde in so kurzer Zeit zu umfliegen, der wird sagen, es kann auf diesem Planeten nichts geschehen, das die anderen nicht auch in irgendeiner Weise betrifft. Es war ja eigentlich nicht meine Aufgabe, aus dem Fenster zu schauen, sondern ich war auf dieser Mission, wie ich schon sagte, verantwortlich, die wissenschaftlichen Experimente anderer Wissenschaftler zu machen. Und das ist ja eine große Verantwortung, denn an jedem Experiment arbeiteten in der Regel mehrköpfige Teams viele Jahre lang. Aber in dem Moment, als ich endlich Zeit fand, aus dem Fenster zu schauen, das war der emotionalste Augenblick meines Berufslebens und auch der Eindruck, der am nachhaltigsten geblieben ist. Dieser Eindruck, den kann man mit Sprache eigentlich nur mangelhaft beschreiben. Man sieht eine schwarze Welt, denn das alles leer. Es ist das finsterste Schwarz, das man sich nur denken kann. Und dann in der Nähe eben die Erde, die einem mit ihrer Schönheit völlig überwältigt. Aber gleichzeitig hat man auch den Eindruck, es ist alles zerbrechlich. Gekrümmter Horizont ist gesäumt von einer hinreißend schönen blauen Schicht, die aber sehr dünn ist und auch zart und zerbrechlich wirkt. Und dann kommt hinzu, dass ja 90 Minuten ausreichen, den Planeten Erde zu umrunden. Und diese Fakten, die ändern die Wahrnehmung. Hat man vorher die Erde als so riesig gesehen, dass sie im Grunde die Vorstellungskraft überfordert. Man kann sie ja nicht als Kugel wahrnehmen. Dann sieht man plötzlich die Erde als ein Raumschiff, mit dem wir alle im leeren Weltraum unterwegs sind.
For many centuries, we were gazing outside of the planet. We looked at the stars, we looked at the sun. You know, the Copernican system. And this made us think in a different way about God, humanity, power, what's our destiny, and so on. It was the outside look that created modernity, if you like. And in a sense, if we look back onto Earth from outer space, which is only possible if you have a space vessel, rockets, things like that, then you may start to think differently about our planet, what we are doing to the planet, what we are doing to ourselves. So I guess it's clearly a paradigm shift. I think the last 50 years have been, in particular, advancement in systems thinking, quite general. Yeah? Many disciplines have not yet understood that. They still think, you know, reducing in size and in focus and so on is the progress of science. But it's the other way around, actually. The progress of science of the last decade was taking the pieces and integrating them back, so to speak, to a holistic understanding. Modern science is systems science, if you like.
これだけど宇宙船地球号っていうことの概念は本当は何なのかと。ですから有限のこういう一つの乗り物に乗り合わせていて、この乗り物がどんな乗り物なのかっていうことですよね。地球システムっていうのは大気があり海がありね、まあ地圏と言いますけれども、大陸近くとか海洋近くとかマントルとかコアとか、こういうのを含めて例えば地圏と呼ぶとすると、地圏とか大気圏とか水圏とかね、あるいは生物圏とか、こういうものが複雑に相互作用しながら地球という星ができてるわけですよ。ね、要するに地球っていう星を研究しようと思ったら全部を一つの結合したね体系として見なきゃいけないと。まあ全て関係してるんですよ。
It's a long-lived planet. It's either a very lucky planet or it's self-regulating in some way. This is one system which will have system properties, which has properties which you cannot analyze by looking just at the biology or just at the physics. We now know that there are some negative feedback type mechanisms that keep the planet Earth relatively stable, that help to stabilize the planet, and they do involve living organisms. We have evolved on the Earth, but for us to be here, we require that the planet has been habitable for 4 billion years, because it takes 4 billion years of evolution for us to get here.
We now know that our ship began with a surface on fire and a toxic atmosphere filled with carbon dioxide. Over eons, our atmosphere evolved, filling with oxygen and cooling the planet.
地球ができた時はドロドロに溶けた地球とその上を覆うですね熱い原始大気とこういう2つの構成要素からできているようなものです。現在の生物と似たような、その一番元になるようなものがたくさん生まれてくるのが今から20億年ぐらい前のことです。でその結果ですね、地表付近には、生物が作り出す環境が生まれます。具体的には大気中に酸素が満ちてきます。
What transformed Spaceship Earth's atmosphere was the relationship between emerging life and our fuel source, the sun.
So, let's have a look. Oh yeah. In general, everything in the universe has to follow the second law of thermodynamics, that is, order is being destroyed more or less by friction and other things, processes, and in the end you have just thermal waste, if you like. Unless you have a constant influx of valuable energy, like sunlight, for example. A system may actually work against the grain of thermodynamics and build ever more complexity. Yeah? That's precisely what is happening in our small corner of the universe on planet Earth. Take the sun away and everything will decay, yeah? And it will all go into a sort of chaotic state again. So the sun is driving everything. The sunlight has instigated in development of what is probably the biggest invention in the history of our planet, that is photosynthesis. So you can take an energy quantum from the sunlight and combine it with CO2, and then you can create sugar plus oxygen. And this is the basic formula for our evolution on this planet. Now, sugar means you can create biomass, of course. You can build higher forms of proteins and all that. It's a long, long story, at least 1 billion years long.
It seems like a miracle And indeed, it is a miracle in a sense. Photosynthesis was invented nearly 3 billion years ago. Imagine what would have happened if photosynthesis had not been invented. We would not be here, that is for sure, and none of this would be here. Plants on the land, like the algae in the oceans, are shaping the overall environment of the planet over hundreds of millions of years. All of the vascular plants today evolved about 350, 400 million years ago. And they take carbon dioxide from the atmosphere, which they use in their photosynthesis, and then in their root systems, they put that carbon dioxide into the soil, and there it reacts with soil and rock, and it is locked up. The effect of these organisms on carbon dioxide over time, that is a big effect. They are acting as kind of cooling agents for the planet. The atmosphere of Earth has 21% oxygen in it, and oxygen is a very reactive gas, and of course it's that reactivity which enables large, complex animals to exist.
The interesting thing is, not only do you create oxygen, but you draw down the CO2 from the atmosphere. That's the interesting thing, yeah? And you draw it down and you store it in biomass and so on. A tree will fall into water, so it cannot be oxidized again. It will sink down to the ground and will be sequestered. And this tiny little part of carbon that is taken out of the natural cycle, that is the source of the so-called fossil fuels. And it takes 500 million years to 1 billion years to create that.
But coal is typically produced from terrestrial plants, swamps, trees, depending on the degree of coalification. Some parts of coal you can see beautifully preserved leaves of ferns, bark of plants, the actual wood in the trunk, leaves, and so forth. So coal came from land, oil and gas generally from the sea. Oil is an organic material, mainly microorganisms, algae. It's been preserved in sediments. Basically, it's buried under heat. The organisms are transformed into oil. If you look at what I collectively call hydrocarbons, which is coal, oil, and gas, we really got started on coal first. Coal back in 1850, which is really the Industrial Revolution. Coal was about 18% of our energy supply at that point. and wood biomass was over 80%. In 1850, that's only 160 years ago, our only fossil hydrocarbon was coal. Arguably, oil got started in Canada, in southwestern Ontario, 1858. We've been using oil for a little over 160 years. And as of the end of 2011, we burned about 1.2 trillion barrels of oil. What is stunning to me about that consumption is that 90% of it has been burned since 1961. And 50% of it has been burned since 1988. So we're now burning 32 billion barrels of oil per year. We're not finding many billion barrel fields. In terms of conventional oil, we're probably burning about 3 to 4 barrels for every barrel we're finding each year. 32 billion barrels of oil every year, it's a lot of oil. If you divide that into what's on the books, that's about 50 years until it's gone. The Earth had a lot of hydrocarbons to go after, but now we're hitting the geological limits. If you look at the traditional coal mining areas like Appalachia in eastern US, production's been declining for years.
The world has a lot of coal. There's no question about that. But here again, how much of that is resource versus how much is reserves? How much of that total resource, which is enormous, how much of that can we extract profitably using existing technology? Well, it turns out probably a lot less than has been estimated in the past. In the US, where we're seeing mountaintop removal coal mining, this is maybe a relatively cheap way of getting that coal out of the ground, but it's also a sign of desperation.
Well, the thin black seam that you see here is coal. Of course, then the other elements here are the rock and sandstone that form the mountain. So the mountains are like a layer cake. So the process of mountaintop removal means that they take all of this top off to get to that little bit of coal. The ratio is 20 to 1, maybe more. There are other ways to get to these seams, not necessarily this one, because it's too thin to mine any other way. But there's no commandment that says that I have to mine every lump of coal in the state of West Virginia either.
Two shots just over here from us. Dust, my God Almighty. They say I'm the only one left that knows anything about this mountain. I'm the only one left. Over the hill there, my grandpa and grandma, we didn't have no power, We didn't have no watches. We had a bell. If she rung it one time, dinner was ready. She rung it 2 times, they's the biggest one. Of course, I spent a lot of time out and underground, 28 years of it. They started this work here about 3-4 years ago. Take the top of this mountain off. And most of this coal now is going overseas, China. Someday they're gonna wonder what happened. There's a better way of getting this coal. You'd have trees. You still have the mountains. Look what they've done. Look what they've done. I mean, for miles. You can see, look over yonder. And just part of it. This is just part of it. I feel awful. It's scraped the bottom of the barrel.
We're inventing better barrel scrapers all the time, but we shouldn't kid ourselves about what's going on. So the world faces a coal supply shortfall as well as oil and natural gas. All through the 20th century, the amount of oil that we were extracting on an annual basis was increasing year after year after year. For the last 7 or 8 years, it's leveled off. And that's not because people aren't looking for more oil. So what's going on there? Well, what's going on is old oil fields are depleting, and rates of production from those old supergiant oil fields that we found back in the 40s and 50s and 60s, those rates of production are declining. When a conventional oil field starts to reach its middle age, let's say, then efforts are usually put into water pumping to force the remaining oil toward the wellbore.
もともと工学系で、資源の探査ですとか、あるいは環境観測というそういう、リモートセンシングと呼びますけれども、そういう技術をやってました。基本的には今の言いました生産の状態というのが地表のですね微細な変動に現れてくると。こういうふうに油田の状況をモニターをしていくと。ここに衛星がございますけれども、宇宙からこれ600キロ700キロ上ですけれども、そうですねビフォーアフターなんですね。最初の地表の状態を観測しておきまして、次に生産に伴ってその後アフターという形で観測します。これクウェートの世界第一、今2番ですかね、のブルガン油田というところですけれども、ですね、実は石油っていうのはどういうところにたまるかっていう非常に乱暴ですけれども、当然石油っていうのは少し水に比べると軽いですので生産をすると。ただその生産する際に、地面の下の通常石油自噴してくるものも多いんですけれども、その圧力の維持を図るために実は周りに別の井戸を掘りまして、そこは実は水を圧入するとかですね、そういうことをして地下のその圧力維持を図ってその真ん中の溜まっている石油をいわばストローで吸い出すという。その石油の生産のピークというのがもうすでに来たと。ということはラフに言って半分、使いを切ったという言い方もできるわけですね。
Conventional oil is already in decline, and we're going to have to find at least 3 Saudi Arabias worth of new conventional oil just to maintain that decline on a very, very shallow level going forward. And the only place to really find a good portion of that is unconventional oil. And that is why we're going after this stuff. There's a concept called energy return on energy investment. You have to use a certain amount of energy to drill a well, to build pipelines to produce the oil. And really that depends on the productivity of the wells that you drill. The net energy yield of drilling a vertical well into the Ghawar field in Saudi Arabia back in the 50s was probably at least 100 to 1. So we invested a barrel of energy to net out 100 barrels of useful energy. Now we're looking on the last frontiers, very deep water. We're using rigs like Deepwater Horizon, multi-hundreds of millions of dollars per well. And so the net energy return on that is probably somewhere around 25 to 1. We're looking also at things like tar sands. Only 20% of the tar sands are shallow enough to be surface mineable, and that's about 5 to 1. 80% are only recoverable by so-called in situ methods that have a net energy return of about 2.9 to 1. We're burning a barrel to net out about 2 barrels of useful energy. We wouldn't be doing that if we had alternatives. If we look at things like tight oil, or shale oil is another synonym for it, the annual depletion rate is 40% per year, not 4% for all of the conventional oil pools. So we have to find enough new production to make up for 40% decline every year to keep production flat. And that requires a lot of drilling and a lot of hydraulic fracturing. Really, if you look at things like tight oil, we're running out of space on the surface to put more wells.
There is a side that's right here, right off to your right. As we drive up here, you'll be able to see it. So straight down the runway, off to the left, there's a tower that's out there. And that's another drill rig. The rig that's drilling out there is drilling under the speedway. They can be fenced in, they can be concealed, they can be bermed up, plant trees around them. They're very nondescript. I mean, you can make them fit into pretty much any environment.
They're drilling about 1,500 wells a year, so that's more than enough. They can offset production and increase production. However, they're going to run out of locations at some point. But if you look at the declines that have to be offset every year, it's a treadmill. More and more and more wells will have to be drilled just to maintain production, let alone grow it. And what that's suggesting is that oil production from the 2 biggest tight oil fields in the world will likely be a bubble that will last maybe 10 to 12 years. Consider that the oil that we're burning today took 500 million years to accumulate. 500 million years of solar energy preserved in that oil. And we're burning 32 billion barrels every year. That works out to about 5 million years worth of solar energy burned every year in terms of our oil consumption, and 14,000 years of solar energy every day. So that tells us one thing that's certain. This is a non-renewable, finite resource. It's finite in terms of the foreseeable lifespan of the human race as a species on this planet.
And this is the big intervention we are seeing now. You have to imagine that what was geologically sequestered and biologically through photosynthesis over 500 million years or more is being released within a few centuries by the Industrial Revolution. So you can call it the Great Oxidation because it happens within a few centuries only.
The burning of fossil fuels is taking Spaceship Earth backward in time to the era of volcanoes, to the primordial atmosphere that existed before complex life arose.
先ほどちょっとゴーさんと話しましたけども、これ CO2 の濃度ですので、観測してますのは大気中の微細な光に対する応答っていうものを見まして、で全体にそのいわゆる大気の中の CO2 の量を測っていくというそういうタイプの技術になります。
You know, it's funny, the more we study the Earth, the more we realize how delicate things are. Life on Earth as we know it has a very small layer of carbon in the atmosphere to thank. The greenhouse effect involves radiation from the sun hitting the Earth and staying wrapped in a warm blanket of carbon that keeps the temperature just right. A Goldilocks scenario that we don't want to mess with. Uh, 350 parts per million is the safe upper limit of carbon in the atmosphere. Right now, we're at 400, much higher than the atmospheric conditions on which civilization developed and that life on Earth is dependent on. Since the Industrial Revolution, we've put enough extra carbon into the atmosphere that instead of a Goldilocks situation with temperatures that are just right in the right places, we're all of a sudden overheating the Earth. It basically means that over time, humanity has burned enough fossil fuels, emitted enough extra carbon into the atmosphere that we have a fundamentally different climate than we've had for the entirety of human civilization. We know that because an atmosphere with a higher concentration of carbon will hold more heat from the sun, and we know that when it holds that heat, it increases the temperature of the Earth, and this has tremendous effects.
We are heating up the planet in an unprecedented way, but we also take away from future generations a benign environment. The environment in which our civilization has been created in the so-called Holocene over the last 12,000 years. We disrupt it completely. That's one thing. Huh? So you change the life support system. And the second is we take away from them the access to cheap energy. If you burn all the precious stuff within a few decades only, yeah? There's nothing left. It's quite easy. Yeah? So what we have to do is we have to find a way to get cheap and, if you like, democratic access for everybody on this planet to energy without harming the environment. It's a very simple formula. It's a no-brainer, really, yeah?
Dieses Raumschiff Erde, das macht es möglich, ein Fenster zu öffnen, frische Luft hereinzulassen. Hier gibt es Jahreszeiten, es gibt blühende Wiesen, spielende Kinder. Es gibt Kontakte zu anderen Menschen. Es ist auch keine gute Idee, die manche predigen, wenn wir die Erde sozusagen ausgelaugt und so beschädigt haben, dass das Leben hier nicht mehr attraktiv ist, dann siedeln wir woanders. Für mich ist überhaupt keine Frage, dass es an keinem anderen für uns erreichbaren Punkt eine Lebensqualität gibt, so gut wie diejenige, die wir hier auf der Erde vorfinden. Wir fliegen alle mit dem Raumschiff Erde in dieser Leere des riesigen All. Es ist ein Raumschiff mit viel, viel besseren Qualitäten als ein vom Menschen erschaffenes Raumschiff